Now we are going to consider C of a comma b, the set of all continuous functions from closed interval a comma b to R. The previous lectures we have defined LP spaces. They are sequence spaces. So now we are going to define function spaces, that is a vector space consisting of functions. So here we are going to consider all continuous functions from closed interval a comma b to R. Now we are going to try to define a norm on these C of a comma b. So C of a b, since it contains all continuous functions, and we know that all continuous functions are integrable, and in LP spaces we have defined P norm, and the same P norm only we have defined in finite dimensional R power n also. So we are going to see whether we can also define a similar norm here in this C of a comma b or C of 0 comma 1. So first we are going to define one norm. So one norm of f, where f is a element of C of a comma b. So f is a continuous functions from a comma b to R. So one norm of f equal to integral 0 to 1 modulus of f of t dt. If it is a function from 0 to 1 to R, we define integral 0 to 1. If it is from any closed interval a b, we can define integral a to b. So now we are going to check whether the C of a comma b with respect to this one norm is complete or not. For that we are going to define a function, a sequence of functions. We are going to define a sequence of functions f1 of x. Before that we let an equal to 1 by 2 plus 1 by n. So an is a sequence converging to 1 by 2. So an is equal to 1 by 2 plus 1 by n, and we define f1 of x equal to 0 for all x from 0 to 1 by 2, and f1 of x equal to n into x minus 1 by 2 for all x belonging to 1 by 2 to an, and f1 of x equal to 1 for all x belonging to an to 1. So we can see that f1 of x is a function from 0 to 1 to R, and also we can see that f1 of x is a continuous function because of the common points. Whenever a function is defined in various domains, we have to check the function at the common points to see whether the function is continuous or not, and we can see that at 1 by 2 n into x minus 1 by 2 will be 0, and so similarly when x equal to an, that is x equal to 1 by 2 plus 1 by n, if we substitute in place of x, we have n into 1 by n equal to 1. So at the common points the function agrees. Therefore all these functions is a continuous function. So f1 of x will be a sequence of continuous functions. So now we try to see whether this sequence is a Cauchy sequence or not. So we are going to calculate one norm of f1 minus fm. So by definition it is equal to integral 0 to 1 modulus of f1 of x minus fm of x, and this integral can be split into half to an and an to 1, because we know that in 0 to half both f1 of x and fm of x equal to 0. Therefore we can split the interval as 1 by 2 to an and an to 1. So by substituting for f1 of x in 1 by 2 to an, we know in 1 by 2 to an it is defined as n into x minus 1 by 2 and m into x minus 1 by 2. So correspondingly we get 1 by 2 to n minus m x minus 1 by 2 dx plus an to 1, and in an to 1 both the functions are defined as 1, therefore 1 minus 1, so that term will be 0, and finally we get n minus m the integration of x minus 1 by 2 is x minus 1 by the whole square by 2, and if you substitute the limit, we have n minus m by 2 1 by n square. So we have n minus m by 2 n square, and since n minus m is less than n, and therefore we have it is less than or equal to 1 by 2n. So 1 norm of fn minus fm is less than or equal to 1 by 2n. Therefore after some stage we can see that this 1 norm of fn minus fm is less than epsilon. Hence this sequence is a Cauchy sequence in C of 0, 1. So suppose if you can find a limit, so we have to check whether this sequence converges to a continuous function. Suppose this sequence converges to a continuous function, then 1 norm of fn minus f, if you define it, is equal to integral 0 to 1 modulus of fn of x minus f of x dx. And if you split the interval, so in the first integral we see that fn of x is equal to 0, so we have only modulus of f of x. The second integral we have modulus of fn of x minus f of x as it is. The third integral we know that fn of x is equal to 1. So since we know the values of fn of x, we can substitute the respective integrals, but we do not know what is the values of f of x is going to take. So we have f of x as it is. Now if fn converges to f, all the integrals should be 0, and since all the integrals contains positive integrands, because we have modulus of f of x the first term, and modulus of fn of x minus f of x the second term, and modulus of 1 minus s, they are all positive integrands. And since if f of x is a continuous function, that means all these integrands should be 0. So all these integrals should be 0 in the interval of integration. So for example, each of these integrals should be 0 in the respective interval of integration. So we have f of x equal to 0 in the interval 0 to half, and for the third term, if you apply, we have f of x equal to 1 in the interval x belonging to 1 by 2 plus 1 by n, comma 1. We need not worry about the interval half to an, because we are worried only about the f of x. So we can just look at this function f of x equal to 0. If fn converges to f, then if f is a continuous function, then f of x equal to 0 in the interval 0 to 1 by 2, and f of x equal to 1 in the interval 1 by 2 plus 1 by n, comma 1. But since 1 by 2 plus 1 by n converges to 1 by 2, and f is continuous, so f of x equal to 1 in the interval half to 1, and this says that f is not a continuous function. Therefore, when we assume that fn converges to a continuous functions, we have something like a contradiction, and therefore f1 cannot converge to a continuous function. Now here we have defined C of 0, 1 in 1 norm, but we can also define C of 0, 1 or C of a, b in any p norm. That is p norm of f equal to integral a to b modulus of f of x the power of p dx the power of 1 by p. So we can see that C of ab can be defined in any p norm. So with respect to any p norm, C of ab will be a non-linear space, but the above discussion tells that C of ab cannot be complete in any p norm. So that is the important thing we can understand from C of ab. It will not be complete in any p norm if you define the norm of fs integral a to b modulus of f of x the power of p d the whole power 1 by 2. So for any p norm, we can say that C of ab is not a complete space. So if you want to make C of ab is a complete space, then we have to look for some other norm, so that C of ab will be made into a complete non-linear space. Now we are going to check that a new norm we are going to define on C of AB is a complete nonlinear space. So we are going to define infinity norm with the same pattern we discussed in R power n and LP spaces. We have infinity norm, and here also we have a similar infinity norm. So we define this infinity norm as supreme of mod f of x, where x belongs to closed interval a comma b. So norm of any continuous function is nothing but the supremum of that function taken over its modulus. Since we know that any continuous functions on a compact interval will be bounded, therefore we can say that supremum exists for any continuous function on closed interval a comma b. So we can see that C of AB is a nonlinear space with respect to infinity norm, and we are going to see whether this infinity norm is a complete nonlinear spaces, because we have already seen that C of AB is incomplete with respect to other p norms. So we are going to check whether it will be complete in this norm. So take a Cauchy sequence in C of A comma B. So given epsilon positive, there exists a capital N such that infinity norm of Fn minus Fm, which is equal to supreme of modulus of Fn of x minus Fm of x, where supreme is varying over A comma B, which is less than epsilon. Now since the supremum itself is less than epsilon, we can fix any x naught in A comma B. So take any point in A comma B, then since the supreme itself is less than epsilon, modulus of Fn of x naught minus Fm of x naught is less than epsilon for all n comma m greater than n. So here we are fixing any point x naught. Now this inequality tells that Fn of x naught is Cauchy. So now here Fn of x naught is a sequence, it's a real sequence, because we have fixed x naught, and when we allow n to vary, so here Fn of x naught will be a real sequence, and from this inequality is a Cauchy sequence. Therefore we know R is complete. Since we have R is complete, it converges to a real number, and we let that real number to be f of x naught, because this limit depends on x naught. We are letting that number to be f of x naught. So this we can do for each x naught in A comma B. Therefore it tells that Fn of x converges to f of x pointwise for each x belongs to A comma B. Okay. So Fn of x is pointwise converges to f of x, where f of x is defined as the limit of each Fn of x. Also, since supreme of mod Fn of x minus Fm of x less than epsilon for all n comma m greater than n, so in this equation we can allow m go to infinity. When we allow m goes to infinity, we have supreme of mod Fn of x minus f of x less than epsilon for all n comma m greater than n. So which implies that Fn converges to f uniformly, because this is a uniform convergence which you know. So if a sequence of functions converges to f uniformly, then supreme of mod Fn of x minus f of x is less than epsilon for all n comma m greater than equal to n. Since here there is no m here, so supreme of mod Fn of x minus f of x is less than epsilon for all n greater than n. So Fn converges to f uniformly, and we know that if Fn converges to f uniformly, then by the property of uniform convergence, this f has to be a continuous function. Since uniform limit of any sequence of continuous functions is continuous, so this limit f of x is a continuous function, and therefore this f belongs to C of A comma B. And not only that, the above inequality shows that Fn of x converges to f of x in sup norm. because supreme of mod f1 of x minus f of x is less than epsilon. Therefore fn converges to f in supranorm. Of course, here we can understand that convergence in supranorm is same as uniform convergence. So we study uniform convergence. So convergence in supranorm is not any new form of convergence, but it is nothing but the uniform convergence of sequences. So we can see that C of AB is a complete nonlinear space, and therefore C of AB is a Banach space, while C of AB, if it is defined with other p norm, it is not a Banach space. So this is the property of C of AB, because in LP spaces we saw that LP spaces with respect to any p norm, okay, is a Banach space, but here C of AB, it does not change with respect to norm. C of AB remains the same vector space of continuous function, only the norm changes here. We don't get different vector space as we obtained in LP spaces, but here only with respect to the infinity norm it will be a Banach space. With respect to other norms it won't be a Banach space, and therefore normally when we say C of A comma B, we understand that it is attached to the infinity norm. Otherwise, if you want to define any other p norm, we specify when and where required. Now instead of taking the set of continuous function, we can very well take the set of integrable functions. And when we consider the set of integrable functions, we can consider either Riemann integral or Lebesgue integration. But since Lebesgue integral is more general than Riemann integration, and we consider the set of all Lebesgue integrable functions. So here what we are doing is we are considering a Lebesgue measure on closed interval a comma b, because to define a Lebesgue integral, first we need to define a Lebesgue measure on closed interval a comma b, and based on that Lebesgue measure we can define a Lebesgue integral on closed interval a comma b. So we can define a similar p norm on these spaces. So we are going to consider the set of all measurable functions, on closed interval a comma b, and similarly we have considered set of all continuous functions in the previous discussion. Now we are considering set of all measurable functions on closed interval a comma b, and this functions we call it as LP of a comma b, because all these functions, that is LP of a comma, depends on that norm p. So to be a member of LP of a comma b, first that p norm has to be defined, that is integral over closed interval a comma b mod f of x to the power of p d mu to the power of 1 by p. Here the integral is a Lebesgue integral, it is not Riemann integral, it is a integral is a Lebesgue integral. And similarly we can define infinity norm of f. We can define infinity norm of f as a essential supreme of mod f of x belonging to closed interval a comma b. So similar to p norms in LP spaces, we can define the same p norms in capital LP space. So this we call it as a capital LP space. The only thing is the capital LP spaces, actually they are equivalence class of functions. That is, we have f equal to g if the set of all points where f of x not equal to g of x has measure 0. So equality is almost everywhere. So f equal to g means f need not be equal to g on the all points, but wherever the function is f not equal to g, if you take the measure of those points, that measure will be 0. So LP of AB is not exactly like a normal linear space, a normal set. It is a equivalence class of functions. So in other words, each element is a equivalence class, and any member of the equivalence class can be used to represent that class, and any member of the equivalence class will be a measurable functions which is contained in that equivalence class containing all the other measurable functions equivalent to that function. That is, f is equal to g if f equal to g almost everywhere, which implies p norm of f minus g is equal to 0. And also LP of a comma b can also be viewed as a completion of C of a comma b for 1 less than equal to p less than infinity. So now we shall see that why we need completion of C of a comma b and what do you mean by a completion of a nonlinear space.